Hello, so this is a revision video for AP Chemistry 8.8, Properties of Buffers. As seen in Chapter 8.4, a buffer is a solution that resists changes in pH when small amounts of acid or base are added. Acidic buffers work by having both a weak acid and its conjugate base in an equilibrium system. Basic buffers work by having a weak base and its conjugate acid also in an equilibrium system. Acidic buffers can be made from a weak acid and a salt that contains the acid's conjugate base. For example, the weak acid ethanoic acid and its salt sodium ethanoate can both be mixed together in solution to create a buffer. You can also prepare a buffer by reacting a weak acid with a limited amount of strong base. For example, if you add an excess of weak acid to a strong base like sodium hydroxide, you will produce a final mixture that contains conjugate base ions from the weak acid molecules left over, and H2O. This produces both Ha and A- in the same solution, forming an equilibrium system. Basic buffers can be made from a weak base and a salt that contains the conjugate acid of the base. For example, if you mix ammonia NH3 and its salt ammonium chloride NH4Cl, you would form a basic buffer system, with the NH3 and NH4+ in an equilibrium with each other. So how do acidic buffers work? An equilibrium is established in the buffer system between Ha, A- and H+, or H3O+. The concentration of Ha and A- in the mixture must be much greater than the concentration of H+. This ensures that equilibrium is sensitive to changes in H+ ion concentration more than changes to Ha and A- concentration. Equilibrium can shift to keep H+ ion concentration nearly constant. Note, to make these equations look slightly simpler, H+ ions are used instead of H3O+ ions. Remember, H+ and H3O+ can be used interchangeably. For example, in the ethanoic acid and sodium ethanoate buffer system, an acid is added, H+ ions are introduced. The CH3COO- combines with the added H+ ions to form CH3COOH. In other words, A- ions accept H+ ions to form HA. This means the concentration of HA increases slightly and the concentration of A- decreases slightly. But the concentration of H+ ions remains nearly constant, meaning the pH of the system remains very similar to what it was before the acid was added to it. Equally, when a base is added, OH- ions react with H+ ions in the solution to form H2O. This causes the position of equilibrium for the dissociation of HA to shift to the right. In other words, CH3COOH molecules dissociate more to replace the lost H+ ions. This means the concentration of HA decreases slightly and the concentration of A- increases slightly, but again the concentration of H+ ions remains nearly constant, the same as it was before the OH- ions were added, meaning its pH remains nearly constant. Exam tip here: remember that the concentration of HA and A- will change when an acid or base is added to the buffer. When H+ ions are added to the mixture, the moles of HA will increase by the same amount as the moles of H+ ions added, and the moles of A- decrease by that same amount. When OH- ions are added, the moles of HA will decrease by the same as the moles of OH- added, and the moles of A- increase by the same amount. As long as there are significant amounts of HA and A- present in the system can buffer against pH changes. Note that the actual exact pH of the solution will change slightly because the concentrations of HA and A- are changing, but the change in pH will be much smaller than if there was no buffer system present. Weak acids and weak bases are needed to make buffer systems because they only partially dissociate, setting up an equilibrium with their conjugates. This equilibrium helps them resist change in pH by the equilibrium shifting, reacting with added H+ or OH- ions. Strong acids and bases fully dissociate, so they don't form equilibrium systems, meaning they can't act as buffers.